Welcome to another deep dive into the hidden mechanics of our universe. Today, we are leaving the solid ground beneath our feet and traveling north, far north, to the frozen tundra of Alaska. We are looking up. Most of us know the northern lights. We think of them as the crown jewels of the night sky, a celestial ballet of neon greens, violets, and crimsons that have captivated humanity for millennia. We understand them as the visible breath of the sun, a bombardment of charged particles funneled by Earth's magnetic field into our upper atmosphere. But amidst these curtains of light, there lies a deeper, darker mystery, one that looks not like a presence, but an absence. They are called the Dark Auroras. If you were standing on the Poker Flat Research Range in Alaska tonight, watching a diffuse aurora, that broad glow-in-the-dark background of faint green covering the zenith, you might see something unsettling. Suddenly, thin, jet-black ribbons begin to snake through the green mist. They curl into spirals, widen into gaping holes, or drift like smoke rings made of vacuum. To the casual observer, they appear as strange, ominous gaps. For decades, scientists dismissed them as optical illusions or simple gaps in the plasma clouds. We now know they are neither. These are not merely spaces where the light is not. They are active structures where the light is being actively suppressed. The Dark Aurora is a distinct, violent, and highly structured electrical phenomenon, a negative image of the aurora that represents one of the most powerful and least understood energy exchange processes between our planet and space. To understand this void, we have to rewrite our mental model of the Earth. We need to stop thinking of Earth as a rock and start thinking of it as a giant electrical component. The planet's magnetosphere and ionosphere form a massive circuit, powered by the solar wind. Like any circuit, there must be a complete loop. The bright, beautiful arcs we love represent the downward leg of this circuit. In visible auroras, electrons precipitate downward from space, crashing into oxygen and nitrogen atoms in the atmosphere, exciting them until they release photons. That is the light. But nature demands balance. For every cascade of electrons coming down, there must be a return current going up. The Dark Aurora is the visual signature of this return current. It is, quite literally, the exhaust pipe of the ionospheric engine. In these dark regions, the electric fields reverse. Instead of a potential drop that accelerates particles downward, there is a divergent electric field that evacuates the ionosphere. It sucks electrons up and out of the atmosphere. It creates a plasma cavity, a literal void, in the electrified air where density drops continuously and light is extinguished. These are the antimatter to the aurora's matter. So how do we study a hole in the sky? This brings us to a significant engineering challenge known as the Ignorosphere. The black aurora forms in the ionosphere, specifically in the E region and F region, roughly 100 to 300 kilometers up. This altitude is a scientific no man's land. It is too high for weather balloons, which pop around 30 or 40 kilometers, and it is too low for satellites, which would drag against the atmosphere and burn up if they flew below 400 kilometers. This region is the turbulent shoreline between Earth's atmosphere and the vacuum of space. It is a zone of chaotic winds, immense electrical currents, and chemical heating. To study it, scientists cannot look from above or below. They must go through it. Enter the sounding rocket. These are not the lumbering giants that carry rovers to Mars. Vehicles like the NASA Black Brant or the Terrier-improved Malamute are the special forces of rocketry. They are relatively small, solid-fueled, and designed for a suicide mission. They launch rapidly, screaming up to 200, 300, or 600 miles in altitude, tracing a parabolic arc through the aurora before falling back to Earth. They give scientists 10 to 15 minutes of apogee, time in space, to taste, smell, and measure the plasma directly inside the event. For the Dark Aurora, the mission profile is harrowing. You are not aiming for the bright, easy-to-see lights. You are trying to hit a moving, invisible target, a black patch in a faint green sky with a rocket traveling at Mach 5. In recent years, the pursuit of the Dark Aurora has shifted from curiosity to a high-priority scientific imperative. Several missions stand out in this bold endeavor. Before rockets took center stage, the European Space Agency's cluster mission provided the smoking gun. In 2001, the 4 cluster satellites flew in formation through a black aurora high above Earth at roughly 20,000 kilometers. They detected a massive evacuation of electrons. But cluster was too high to see the complex turbulence happening on the ground in the ionosphere. It saw the chimney but not the fire. That required getting closer. This led to missions like Mica, launched from Alaska. Mica was a detective looking for the fingerprint of the Dark Aurora's cousin, the discrete arc. It proved that alpha waves, ripples in the magnetic field lines, act like guitar strings, communicating energy between the magnetosphere and the ionosphere. This established the language that the Dark Aurora speaks. But the most audacious mission concept in recent years is NASA's BADASS. The acronym is as aggressive as the science. It stands for Black and Diffuse Aurora Science Surveyor. The goal was to fly a rocket specifically through a black aurora event. This is incredibly difficult because black auroras are elusive. They often appear late at night, in the recovery phase of a substorm, when the sky is a messy, pulsating glow. The badass rocket carries a suite of instruments, including Langmuir probes to measure electron density and temperature, energetic particle detectors to count the electrons fleeing the atmosphere, and vector electric field instruments to map the invisible walls of the void. The science here is trying to solve a major discrepancy. Theory suggests the black aurora should be stable, yet ground cameras show them swirling, fragmenting, and curling. Scientists want to know if this is the Kelvin-Helmholtz instability, the same fluid dynamics that create wave-like clouds in the sky, occurring in a plasma vacuum. Another critical mission is GIRAFF, ground imaging to investigation of auroral fast features. While Badass hunts the dark, GIRAFF hunts the flicker. Launched into pulsating Aurora, which is often the background canvas for black aurora, this mission studies how high-energy electrons from the radiation belts are dumped into the atmosphere. The fast features it studies are the rapid heartbeats of the ionosphere, providing the context needed to understand why the heart sometimes stops beating, resulting in the black aurora. So what happens when a rocket actually pierces the void? When a sounding rocket like Badass enters a black aurora, the data it returns paints a chaotic picture of negative light. First, the onboard Langmuir probe usually screams a warning. It detects a massive density drop. The plasma density can plummet by a factor of 10 or more. The rocket has effectively entered a hole in the ionosphere. Then, the particle detectors see something strange. In a normal aurora, they would be detecting a rain of electrons falling down. In the dark aurora, they detect a fountain of thermal electrons moving up. These are cold electrons, dragged out of the ionosphere by a strong upward electric field. Perhaps the most fascinating data point is the potential hump. In a normal aurora, there is a potential, well, a U-shape in voltage that accelerates particles down. In the dark aurora, the rocket flies through a potential hump, an inverted U. This hump acts as a barrier to incoming solar electrons, blocking the light, and simultaneously acts as a vacuum cleaner for earthly electrons, creating the return current. Recent research, bolstered by citizen science and rocket data, has even revealed the anti-black aurora. These are tiny, intense beads of light that sometimes form inside the black currents. They are a paradox within a paradox, a spark of light inside the shadow. Sounding rockets suggest these may be caused by extreme turbulence at the edges of the black streams, where the shear forces between upward and downward currents rip the plasma apart, creating short circuits of intense energy. You might be asking, why does this matter? Why spend millions launching rockets into the dark? There are three critical reasons. First, the satellite drag mystery. The ionosphere is the medium through which low Earth orbit satellites fly. When the aurora heats the atmosphere, it expands, increasing drag on satellites. This phenomenon famously doomed dozens of Starlink satellites in 2022. However, the dark aurora represents a region of cooling and density depletion. To model the orbit of a satellite accurately, you cannot just model the heating, you must model the holes. Flying through a black aurora is like a boat suddenly losing the water beneath it. Second is GPS scintillation. The edges of the dark aurora are jagged and sharp. When a GPS signal from a satellite passes through these sharp density gradients, the signal is bent and scattered. This is called scintillation. It can cause GPS receivers on the ground to lose lock or report errors of meters to kilometers. In an era of autonomous cars and precision drone warfare, a black aurora can be a massive disruptor. And finally, there is the universal context. The dark aurora is likely a universal phenomenon. It probably occurs on Jupiter, Saturn, or any planet with a magnetic field and an atmosphere. By studying it on Earth, we are learning about the fundamental electrodynamics of the universe. We are learning how planets breathe electricity. The future of sounding the void is bright, or perhaps I should say, appropriately dark. The era of the sounding rocket is entering its golden age. Future missions are moving away from single rockets. We are now seeing swarms, one main rocket releasing several daughter payloads. These can measure the black aurora at multiple points simultaneously, creating a 3D map of the void. We are also using chemical tracers. Some rockets release trails of trimethyl aluminum or barium. These colorful clouds drift with the neutral winds and ion drifts, allowing scientists to see the invisible winds and electric fields twisting around the void. The dark aurora serves as a humbling reminder that in space physics, what you don't see is often as important as what you do. It is a phenomenon of subtraction, a cosmic silence amidst the noise of the geomagnetic storm. The sounding rockets that pierce these voids are our needles, stitching together the fabric of our understanding. They launch into the freezing Alaskan night, trailing fire, to touch the cold, dark emptiness where the Earth exhales its electric soul. In that darkness, we find the balance of our world. the return current that completes the circuit, the shadow that defines the light. The black aurora is not just a hole in the sky, it is a window into the hidden machinery of our planet. And finally, there is the universal context. The dark aurora is likely a universal phenomenon. It probably occurs on Jupiter, Saturn, or any planet with a magnetic field and an atmosphere. By studying it on Earth, we are learning about the fundamental electrodynamics of the universe. We are learning how planets breathe electricity. The future of sounding the void is bright, or perhaps I should say appropriately dark. The era of the sounding rocket is entering its golden age. Future missions are moving away from single rockets. We are now seeing swarms, one main rocket releasing several daughter payloads. These can measure the black aurora at multiple points simultaneously, creating a 3D map of the void. We are also using chemical tracers. Some rockets release trails of trimethyl aluminum or barium. These colorful clouds drift with the neutral winds and ion drifts, allowing scientists to see the invisible winds and electric fields twisting around the void. The dark aurora serves as a humbling reminder that in space physics, what you don't see is often as important as what you do. It is a phenomenon of subtraction, a cosmic silence amidst the noise of the geomagnetic storm. The sounding rockets that pierce these voids are our needles, stitching together the fabric of our understanding. They launch into the freezing Alaskan night, trailing fire, to touch the cold, dark emptiness where the Earth exhales its electric soul. In that darkness, we find the balance of our world, the return current that completes the circuit, the shadow that defines the light. The black aurora is not just a hole in the sky, it is a window into the hidden machinery of our planet.